Let's investigate vector spaces. In this video, I'm going to write down the vector space axioms. These are the fundamental properties that every vector space must satisfy. So if we have some abstract algebra structure that satisfies these axioms, then we can call it a vector space. Let's go over some notation. I'm going to use capital V to denote the vector space. And capital F is going to denote the scalar field. So to define a vector space, I need this scalar field. The elements of a vector space are called vectors. So vectors live in the vector space. The elements of the scalar field are called scalars. And these scalars are given that name because they're going to be used to scale vectors. So that is the reason we have this field. This field is going to be a source for all of these elements, these scalar elements, and we're going to use them with these vectors to create scaled versions of vectors. So we'll talk about scalar multiplication later in the video, but first I want to talk about vector addition. I want to write down the axioms for vector addition. So I'll start off with closure. For all vectors u and v in the vector space, capital V, the sum of u and v has to also be an element of the vector space, capital V. So that's what this is saying. I'm using the for all symbol here. That's the upside down A. That means for all. And for all of the vectors, I'm putting an arrow on top. Now that's just to distinguish them from the scalars. So the scalars are not going to have arrows on the top, and the vectors will always have a vector, vector arrow on the top. That's just a neat notation that's going to help us distinguish which elements we're talking about. So vectors are elements of the vector space, scalars are elements of the scalar field. So what is this property telling us? It's telling us that vector addition is closed. If we take two vectors in the vector space and we combine them using the operation of vector addition, we will get another vector that is also in the vector space. So closure is an essential property. Sometimes it's not written down as a fundamental axiom because it can be encapsulated in the definition of the operation. So the operation can be defined to have that closure property. But I'm explicitly writing it out because it's such an essential property for this operation. Next, let's have a look at the associative property for vector addition. For all u, v, and w, which are elements of the vector space, I want the sum of u and v, which is then added to the vector w. I want that to be equal to u plus the sum of v and w. So what is the difference between this side and this side of the equation? Over here, I'm evaluating the sum of u and v first, and over here, I'm evaluating the sum of v and w first. So the order in which you evaluate these guys, the groupings, does not matter. So these brackets are just saying the groupings of these sums. That is the associative property. Now notice that the order in which I'm writing these vectors is exactly the same on both sides. I'm not changing the order of these vectors. I'm just changing the order in which I evaluate the sums. So over here, I'm grouping these first two elements together. I'm evaluating them, and then I'm combining them with the third element. And on this side, I'm first evaluating the sum of the second and the third element, and then I'm evaluating the sum of that result with the first element. So that is associativity for vector addition. Now, let's have a look at another property. That is the identity property. I'm going to say that there exists, I'm going to use this symbol over here. The backwards E means there exists. There exists a zero vector. That is the additive identity. And it is an element of the vector space. Such that, so this colon denotes such that for any vector v in the vector space, if I take v and then I add to that the zero vector, I get back the original vector. So adding the identity doesn't change anything. There is no effect. That is the definition of the identity element. So we have an identity element here. We have an additive identity specifically because the operation is vector addition. Now, I'm putting an arrow on top of this 0. This is a very important arrow, because this arrow is going to help us distinguish that this 0 is an element of the vector space. There is another 0, and it's not an element of the vector space, it's a member of this field over here. So this field has a 0 element, and that 0 element is distinct from this element over here, because that element lives in a completely different space. This is in the field, whereas this is in the vector space. So this vector is not even related to this field. It's not a member of that field, but it has similar properties. It has this same property that we found when we were writing down the axioms for a field, and also the axioms for a group. Now that we have an identity element, we can define inverse elements. So let's do that. For all vectors in the vector space, I want there to exist an inverse vector. And I'm going to denote that by negative v, or minus v. That's also an element of the vector space. So for all vectors in the vector space, I want there to exist an inverse vector in the vector space, such that if I add this vector to its inverse, that gives me back the 0 vector. So adding the inverse gives back the additive identity. So this is just like what we saw in fields and in groups. So we have this inverse property. And these axioms are actually sufficient to form a group. We have the properties of a group over here. So closure, associativity, the existence of an identity element, and the existence of inverse elements for all elements in this group, that actually forms a group. And we want this to be not just a normal group, we want it to be a special type of group, a commutative group, which is also known as an abelian group. So for that, we need the axiom of commutativity. And I'll write that over here. So for all u and v that are elements of the vector space, I want u plus v to be equal to v plus u. So the order in which I add these guys together does not matter. U plus v is the same as v plus u. So with this additional axiom over here, with this axiom of commutativity, now I have a commutative group under vector addition. So this is just half of the story. This is just the addition part of the story. Now we have to go to the scaling part of the story, because vector spaces don't just have addition, they also have that scaling operation. So we're actually going to have some analogous axioms for scaling. We're also going to have closure. So let me define this scaling operation. First, what I want to do is I want to take any vector v. So let me say for all vectors v in the vector space, and for all scalars alpha in the scalar field, I want to combine these two elements together using the operation of scalar multiplication. So I'm going to get alpha times this vector v. I want this to also be an element of the vector space. So we need to be very careful with this notation over here. You can see in all of these axioms, I've consistently been writing element of capital V. So over here, it appears all over the place. We have an element of the vector space, because these guys are all vectors. There's no scalars in these axioms. But in this axiom over here, we have a scalar being introduced. So that scalar field is a source for those scalar elements. And we're pulling those elements in, and we're using them to scale our vectors. So this is telling me for all vectors in the vector space and for all scalars in the scalar field, if I combine these two elements together and form a scaled vector, that is also in the vector space. So that is closure. Scalar multiplication is closed, just like vector addition is closed. So these are analogous axioms. Now, what about this axiom over here? This is associativity. Is there an aversion for scalar multiplication? Well, there is, and that's the associative property for scalar multiplication. So let's write that down. So for all vectors in the vector space, and now we're going to need two scalars. We're going to need for all alpha and beta that are members of this scalar field. I'm going to write down this associative property. So what you can do is you can scale a vector that's already been scaled. And that's the same as taking those two scalars and combining them into one scalar. And then using that one scalar to scale the vector. So this is the associative property for scalar multiplication. But there are some nuances over here. This is not the same type of multiplication appearing on both sides of the equation. Now, to have a simple and elegant notation, I'm using plus signs to denote addition, and then anytime we're multiplying elements, I'm just writing them next to each other. I could also put a dot or a cross, like a times symbol. I could put that in there, but I don't think that would actually add anything. That would just put clutter. We'd have too many symbols. What I want you to notice is that this multiplication and this multiplication are not the same type of multiplication. Let's have a look at this multiplication. We have a scalar and another scalar. So these Greek letters I'm using to denote scalars. They do not have arrows above them, so they are scalar quantities. They are members of the scalar field. And the scalar field has an operation of multiplication that is inherited from here. So this is actually combining two elements together and giving us another scalar. That's the type of multiplication we're dealing with over here. So it's scalar, scalar gives another scalar. What about this multiplication? Here we have a scalar and a vector, and that's giving us another vector. So we have scalar, vector, and the output is a vector. And then when we evaluate this, we're going to have another scalar acting on this vector. So then we're going to have scalar and vector, that's going to output another vector. So that's a totally different type of multiplication over here. But we're using the same notation. We're using the notation where we just put them next to each other, and that is implied, because the context tells you what's going on. So this is associativity. The order in which you group these guys together does not matter. So it's analogous to this associativity over here. But in this associativity, this addition operation is exactly the same. So this is the same plus sign for both of these guys. But over here, this multiplication is not the same. Now, let's have a look at an analogous version for this identity operation. So over here, we have an additive identity. Now we're going to have a look at a multiplicative identity. So for all vectors in the vector space, I want multiplication by 1 to have no effect. So have a look at this. This seems pretty reasonable. If you take 1 from this scalar field and you use it to scale the vector, you get back the vector. So you don't actually change anything. It's analogous to this. If you add an identity element that's an additive identity, you're not going to change the vector. Analogously, if you scale this vector by the multiplicative identity, you will get back this vector. But remember that this multiplication is scalar multiplication, where we're scaling a vector. This takes in an input which is a vector and an input which is a scalar, and it spits out another vector. This type of multiplication is the same multiplication that appears in this line and in this line over here. So this multiplication, and this multiplication are the same operation. But it's not the same multiplication that appears in these brackets. This is a scalar times a scalar. There's no vector over here. That's just inside those brackets. Now, let's have a look at two final properties. These are distributive properties. So when we were defining the axioms of a field, we just had one distributive property that linked together addition and multiplication. Sometimes you can also write it as distributivity from the left and distributivity from the right. But because commutativity is present for both addition and multiplication in a field, you don't have to worry about putting it on the left or putting it on the right. It's exactly the same. And now what we're going to do is we're going to introduce two types of distributivity. One of the distributivity axioms is going to involve the addition of scalars, and the other one is going to have the addition of vectors. So let's have a look at those two guys. So they don't have an analogous pair on this black side of the board. So let's have a look at this. For all vectors in the vector space, and for all scalars alpha and beta in the scalar field, if I take the sum of alpha and beta, and I use that sum to scale a vector, that's the same as individually scaling the vector with both of these guys. So that's the same as alpha times the vector plus beta times the vector. So let's have a look at the operations that are present in this line. So we are sourcing one vector from the vector space and two scalars from the scalar field. So alpha and beta are those two scalars. In these brackets over here, we have a type of addition, and that is scalar addition. That's alpha plus beta. So this plus sign is not the same operation as the plus sign that appears in these black axioms. These black axioms have a vector and a vector forming another vector. So that's this type of addition. That's vector addition. Whereas this is scalar addition. We have a scalar plus a scalar, and that gives us another scalar. So when we evaluate this sum, we're going to get a scalar, and we're going to use that to scale this vector. And then we're going to have scalar multiplication. We're going to scale that vector. But on this side, what we're doing is we're individually scaling this vector by alpha over here, and we're individually scaling it by beta. And then once we've scaled it, we add it together. We find the sum. So that is what this axiom is telling us. Now let's have a look at a very similar axiom, but it's not quite the same. So we're going to need two vectors for this one. So let's take u and v to be our vectors in the vector space. And we're just going to need one scalar for this axiom. So let's take that to be alpha. And alpha is in the scalar field. So we have u and v in the vector space and alpha in the scalar field. Now, if I take alpha and I use that to scale the sum of u and v, that's the same as individually scaling these guys. So we have alpha scaling u, and then we have alpha scaling v. So you can see that this is similar. It has a similar form, but it's not quite the same. Over here we have the same vector appearing, and over here we have the same scalar appearing. There's two different vectors over here. So what is going on over here? This type of addition is vector addition. We're taking in two vectors, and that spits out another vector. And then we're using this scalar to scale that vector. That's the same as individually scaling by alpha and individually scaling by alpha over here. But we're scaling two different types of vectors. So these vectors are both inside the vector space, but they don't have to be the same. That's why one is called u and one is called v. So if you scale them and then sum them, that's the same as this side. That's the same as taking the sum and then scaling. So this can be thought of as distributing this alpha to each of the vectors. And this over here can be thought of as distributing this vector to each of the scalars. So both of these are distributive properties. There are two types of distributive laws. One is a distributive law for scalar addition, and one is for vector addition. These are all the axioms for a vector space. And you can see that a lot of them are analogous. They have another copy for the other operation. So the operation that is occurring in these black axioms is vector addition. And the operation over here, or the most important operation, is scalar multiplication. But you see different types of addition appearing as well. So just remember that this plus sign and this plus sign are not the same type of plus sign. And this plus sign over here, this is adding two vectors together. And this is also adding two vectors together. But this plus sign is adding two scalars together. This plus sign is the same as the plus sign that appears over here and over here. We're adding two vector quantities. But only in this bracket over here are we going to get two scalars being added together. So always look at the context. Look at what's around that plus sign. And always look at the context for multiplication as well. What are the two quantities that are being multiplied or added? That will determine which operation you're dealing with. So you could, in principle, you could actually define two types of plus signs and two types of multiplication signs. But I think that would be way too cluttered, and it's much easier to just look at the context, and that's going to tell you all the information that you need. So we have an abelian group under vector addition, and then we have these additional properties when we have to scale the vector. So that's when we take a scalar from the scalar field and we use it to scale a vector. Those are the fundamental properties. Now let's have a look at an example. So an example is still going to be pretty general. We're going to have a look at a general example, but it's actually familiar to the vectors that you're used to dealing with in 2D and in 3D. So the example that I'm going to state is going to be a field raised to the power of n. So f superscript n. I'm going to define that as the set of all n tuples. So I'm going to use x1, x2, and so on. I'm going to have some dots over here, all the way up to xn. So this is an n tuple. An n tuple is a thing in maths where you just have an ordered list of numbers. So if you swap these guys around, you get a different element. And if you have a double or a triple or a quadruple, that's a type of n tuple. So n is just a positive integer. So you can have 1, 2, 3, 4, and so on. But this is a finite number. We have a finite number of elements in this n tuple. So we're going to define this as the set of all n tuples such that all of these numbers that appear in the n-tuple, x1, x2, all the way up to xn, all of those guys are elements of that field. So over here we have the field. I'll close this bracket over here. Over here we have the field, and over here we have the vector space. So Fn is the vector space over here, but F is the field. And you can take the special case where n is equal to 1, then this field can be used to define a vector space. So you can just have, you could put real numbers here, complex numbers, or rational numbers as well. And that could be your F. And n can be any of these positive integers, 1, 2, 3, 4, and so on. So let's have a look at how vector addition and scalar multiplication are going to work. So we're going to define some vectors. So u, I'm going to call u a vector. That's going to be u1, u2, ... all the way up to un. And this is an element of f superscript n. So it's an element of the vector space. And let's define another vector v. So we have v is another vector. That is equal to v1, v2, ... all the way up to vn. That's also an element of this vector space fn. And let's also define a scalar. So this is a comma, a scalar alpha. And alpha is an element of the field. So it's not an element of the vector space, it's an element of the field. So if we want to add two vectors together, u plus v is going to be equal to, each of the components are going to be added individually. u1 plus v1, then we're going to have comma, u2 plus v2, ... We're going to go all the way up to the nth term. That's going to be un plus vn. So that's how vector addition works. And what about scalar multiplication? If we want to scale a vector by alpha, that's the same as individually scaling all the components. That's alpha v1, alpha v2, we have a comma, ... all the way up to alpha vn. So you can actually think of a special case of this, and the special case would be Rn or R3. So this F, write this down over here, F can be a lot of the common fields that we were dealing with. It can be the rational numbers. It can be the real numbers. It can be the complex numbers as well. And then if you put an n over here, you can have Fn is the rational numbers n, Rn, or Cn. And in quantum mechanics, we're going to be dealing with this one over here. These are complex vector spaces. And a lot of the time when we're dealing with spatial coordinates, we're going to be dealing with these guys. And these guys are called Euclidean vector spaces. So you can define all of that geometry that you're used to in 2D and 3D space using this over here. So what I've done over here is just defined how vector addition and scalar multiplication work. It is element-wise. You take all the corresponding elements and you add them together when you're doing vector addition, and you scale each of the individual elements by themselves. So this is a general example that works for any of these fields, but you can also put it, you can turn this into a specific example that you're familiar with. This is those 2D or 3D vectors by changing this field to the real numbers and changing this n to 2 or 3. That's going to give you, I'll write that underneath. So a special example, e.g. R2 or R3. So this is where three-dimensional arrows live, and this is where two-dimensional arrows in the plane live. So this is when we're talking about the Cartesian plane, and this is when we're talking about XYZ coordinate systems. So that's in 3 dimensions. So all of those guys can be used to define vector spaces. But this is just a vanilla vector space. This is just the basic axioms that are required for a vector space. You can also put additional properties. You can have inner products, and you can have additional axioms. And then you can turn a vector space into something that has a lot more structure to it. And in quantum mechanics, we're going to be dealing with inner product spaces. So an inner product is a way of defining how you can measure distance in a vector space. You can measure distance, and you can see how similar vectors are to each other. Even in these spaces over here, these Euclidean spaces, you can define dot products. So you can see that the structure is a lot more rich than just these axioms. These are just the most fundamental axioms. You can define dot products which take two vectors and spit out a scalar. So a dot product can then be generalized to an inner product. And an inner product also satisfies a bunch of axioms. And we'll talk about that in later videos. And inner product spaces are used to define Hilbert spaces. And Hilbert spaces are where the state vectors live in quantum mechanics. So Hilbert space the Hilbert space is one of the most fundamental concepts in the mathematics of quantum mechanics. So that's why we're defining a vector space over here, because we're going to use this vector space to define an inner product space, and then we're going to have an additional axiom that is called completeness, and then we're going to use that to define a Hilbert space. And Hilbert spaces are a fundamental tool for describing the states in quantum mechanics. That is where the states actually live. They live in Hilbert spaces. So in this video, I wrote down all of the axioms for a vector space. In black over here, you have all the axioms for vector addition, and in blue, we have all the axioms for scalar multiplication. And those scalars are sourced from a scalar field. And that scalar field can be one of these familiar scalar fields. This in red over here is just an example of a general vector space defined in terms of this field. And it's just n tuples. These are the elements of this vector space. And we've seen that if you define the vectors in such a way, and the scalars in such a way, you can have vector addition and scalar multiplication. This is not the only type of vector. Vectors can be far more general objects. They can be functions. They can even be matrices. So elements of vector spaces can be very, very general objects. The only thing that you need for it to be called a vector space is these axioms. So as long as these axioms are satisfied, you can call your abstract algebra structure a vector space. For more videos about abstract algebra, and specifically quantum mechanics, make sure to check out the quantum mechanics playlist. You can find more videos over here.